so a solid is formed with rectangular cross sections perpendicular to the y-axis. The height of each rectangle is 3 units. The base of the solid is the region bounded by y equals 1 over x, y equals 1, y equals 4, and x equals 0. Find the volume of the solid. So it's a good idea here on all of these, if they don't give you a graph, to sort of come up with something for a graph. Now, like I've said a few times, a lot of times they make it calculator active so you can graph it, or they give you a picture of the graph. But in case they don't, I think it's good for us on the notes to try to come up with a graph on our own here. Now, there's something different about this problem. Well, two things that are different about this problem. The first is that our cross sections are perpendicular to the y-axis. Okay, the two that we did yesterday were perpendicular to the x-axis. So we are going to have to, when we see this, we are going to have to do this problem in terms of y. That means we're going to have a dy. We need everything to be y's. That's what this tells us. We also see that we do not have square cross sections this time, right? We have rectangular cross sections, and the height of each rectangle is 3 units. So we are not starting with s squared on this one. So all of those things let's keep in mind. But first let's graph. So I like to graph my straight lines first. Y equals 1, what type of line is that? Horizontal. It's so easy to get those mixed up, and it can be the end of you on doing these problems. So y equals is horizontal. All of the, oh gosh, here's 1. Right, here's 1. Y equals 1. And then y equals 4. We'll do that one in green. And then x equals 0. That one's vertical. It is just the y-axis here. And then 1 over x, that one, we may or may not know what it looks like. It does like this, like in the third quadrant it does like this, in the first quadrant, which is what we care about, it does sort of like this. Since we probably are not that great at knowing what 1 over x looks like, let's just make a table. Okay? Can I plug in 0? No. I can't plug in 0. This graph has a vertical asymptote at 0. So I can't plug in 0. I could plug in 1, and if I plug in 1, what will I get? 1. So I got the point, right here's 1, right here's 1. So I got the point 1, 1 is on this graph. If I plug in 2, what do I get? 1/2. So 2, 1/2. I'm already, like right here, I'm already down below the graph, right? Like down below that bottom line. So I really need like a number over here somewhere. What x value could I plug in? Let's plug in 1/2. So that means I'm doing 1 divided by 1/2. And dividing fractions is easy as pie. Flip the second and multiply. What do I get here? 2. So I got the point 1/2, 2. I'm going to do 1/4. Just to make sure like what I'm thinking is going to happen is going to happen. So 1 over 1/4 is going to be 1 times 4 over 1, and that is going to give me 4. So the point 1/4, 4 is like right here, and that'll be good enough for us to see what's going on with this graph. here. So our area for our base is this right here. Okay, and I now need to think about what I'm drawing here, like what type of like rectangles am I making, right? So so yesterday we actually took those like little pieces and cut them out and glued them on there, right? So what's happening here is I am gonna pick a spot wherever. Let me use purple here for my S. I'm gonna pick a spot. I'm gonna put it right here, but I could pick any horizontal line right here, anything perpendicular to that y-axis, right? And I'm gonna say that is my S, that length of the side and the base, right? And what I'm doing is I am cutting out a little rectangle, right? And the base of that rectangle is going to be S. What is the height of the rectangle going to be? 3, right? So every rectangle that gets cut out is going to have a height of 3 and a base of S. So what's going to happen with this is it's going to be flat on the top, right? Because all the rectangles have the same height. So it's going to be sort of like a prism with this weird shape on the bottom. Have any of you swam at the Greensboro building there? It looks like you could really do some good finding the volume using this sort of stuff with a problem like this. And I even emailed the people like from there asking them if they could give me the dimensions of the building. And somebody emailed me back and did like say, we don't have it, but you can contact these people. And I was like, yes, I might actually get this information. But then the other people never emailed me back on anything. So if I'm ever by there with nothing to do, I'm gonna at least pace it off and try to get some rough estimates on that, because like some of those really cool looking buildings, I feel like these sort of things apply sometimes to them. And I think that one would be like this. So we've got for our area formula, right? Our area, and I'm going to do A of y this time because we're perpendicular to the y-axis, so we have to be in terms of y. A of y is going to equal, we're thinking about the area of this rectangle that I've drawn in, right? What is the area of that rectangle? 3s. Okay. If this was a square, it'd be s squared, right? Because it'd be s times s. But in this case, it is not. So this is one way that this problem is different, right? We're starting with a different area formula. Now, our s value that we have marked here, we have to find it. Since this is horizontal, we have to do right minus left to figure out how wide that value is. Also, everything has to be in terms of y. Is this equation right here that we have for this black line, is it in terms of y right now? Like, is it going to be, like if I used f of x instead, I've got f of x equals 1 over x, right? This is in terms of x because x is the independent variable, the one you're plugging in here. I've got to resolve this for the y instead so that it can be in terms of y. So what I'll do right here is this is 1 over x. I'm trying to solve for the x instead. So I'm going to multiply both sides by x. There. X times y equals 1. And then what do I do? To get that x by itself, divide by y. So x equals 1 over y. This is a function that is its own inverse, really. So you kind of end up with the same thing, right? So this graph right here, I could call it y equals 1 over x, but I need things in terms of y, so I'm going to call it x equals 1 over y. So to find that S value, I'm doing, if it's a horizontal, do right minus left. If it's vertical, do top minus bottom. So the right side is on that black line, and that value is given by 1 over y. What about the left side of that line S, this left endpoint right here? It's not 1. It's on the blue line. What was the blue line? It was 0. So again, I've still given you one where we get 0 right here. So S is just 1 over y. Here. Okay, so just like we were doing yesterday, S gets plugged in to our equation. So A of y equals 3 times 1 over y, which I'm just going to go ahead and call that 3 over y. Okay, so if I do 3 over y, that will give me the area of whatever rectangle where I'm at, right? What I want to do is take all the rectangles that are possible in between 1 and 4, and I want to add them together. To do that, I'm going to use an integral, right? Because that adds all those little pieces together. So I'm going to integrate 3 over y dy. What should my limits be? 1 and 4. Because if I have a dy right here, which axis do I look at? Y-axis. So lowest is here at 1, highest is here at 4. It is not 0 to 1, which is what a lot of people will do because you're thinking about the x-axis. Because we usually do a lot more problems with the x-axis than we do with the y. But we're doing y-axis, lowest is 1, highest is 4. Everybody okay here? Okay, this one's actually pretty easy to integrate if we remember our integral rules. What do we get when we integrate 3 over y? 3 natural log of y. Absolute value of y, I guess. So 3 natural log absolute value of y. And we will evaluate that from 1 to 4. And then we will plug in 3 natural log of 4 minus 3 natural log of 1. I can drop the absolute value bars now because both of those numbers are positive, so they wouldn't do anything even if I left them. They are almost definitely not leaving the answer like this. Why? Natural log of 1 is 0, so I can do just 3 natural log of 4 minus 0, which you don't have to write down, which is 3 natural log of 4. Now, on a free response question, though, you actually can leave it like this on FRQ. You don't have to simplify that any further. On a multiple choice, there is a chance they may not leave it like this either, which I feel is cruel. But sometimes they don't leave it like this either. I've seen some questions where they don't leave it this way. Here's what they sometimes will do. Really, they could go either way on this, but this is the direction I think they usually go on the questions I've seen. Natural log of 4 is the same as natural log of 2 squared. And that square can come out front as a coefficient. So that's 2 times 3 natural log of 2, which gives you 6 natural log of 2. Definitely don't ever do that on a free response question. Leave it 3 natural log of 4 if you got that far, right? But I just thought I'd show you that because I have seen some multiple choice questions where they do that. I guess, yeah, there is a chance they would do that. I think it's less likely, but they could pull the 3 up here and make it natural log of 4 to the 3rd, which is natural log of 64. So it could go that direction also. The questions I've seen before, though, went more this direction. You know, I'm okay with this, and definitely on free response, don't do any of this crazy stuff. But It's evil geniuses coming up with these problems. And they're like, you know what? This problem is easy. The children will get it without effort. Let's make it hard. And then this problem's really not easy, but like the integrating part, if you remember your natural log rule, is pretty easy on this. All right, questions? All right, I got a couple more I want us to look at. All right, so region R is bounded by x equals the square root of 9 minus y squared and x equals negative 1/3 y plus 1. A solid with a base R has square cross-sections that are perpendicular to the y-axis. Write but do not evaluate an integral expression that gives the volume of the solid. You'll see them do this a lot, write but do not evaluate. So they want you to write the integral, but you don't have to actually integrate it. In this particular case, you can see it's going to be a pretty bad integral, right? Possibly even one we don't know how to do without a calculator. So they'll do this pretty often. But the setup is still kind of difficult on this, right? If they give you this, they may or may not give you a graph. Let's prepare for the worst case scenario in which they do not give us a graph. Okay. They don't give us any vertical or horizontal lines right here, which tells me that these two lines must like intersect in some way, that they enclose themselves, right? Let's try to come up with a graph. We may still have to do more to figure out what those intersection points are. I'm going to start over here for this one. What type of graph is that right there? It's not in the form that we usually see it in, but it's a very common type of graph. If I switch my x and my y's, what would it be? It'd be linear. It's still linear here. So inverse of a linear is linear, so it's still linear. So you have a couple options here. You can make yourself a table, or you could just solve it for y and graph that because it's easier to graph a line that way. Let's say that we're not thinking that, though. Let's make a table. Remember, for these type of tables, you need to plug something in for y, right? And I am noticing that if I plug in like 1, I'm going to get a fraction, and I'd rather not have a fraction, right? So let's pick some numbers to plug in here that are going to give us whole numbers. Like, instead of plugging in one, like -1, let's plug in -3, right? If I plug in -3, I will have -1/3, oh bless you, -1 times -3, or sorry, -1/3 times -3, which gives me +1 plus 1, that'll give me 2. I'm going to plug in a 0. So I got, that'll just give me 1 for my x coordinate. I'm going to plug in a +3. That'll be -1 plus 1, which will give me 0. This is probably enough points, especially if you recognize this as a line, to be able to graph this. So I've got 2, -3. I've got 1, 0. I've got 0, 3. And then if I need to go out further, this is just a straight line, so I can just do this. Okay, so there's one of them. Then our other, let's make us a table here. Now, because I've been a math teacher for a long time and we did a lot of conic sections, I know what this one is, but I'm pretty sure you guys have no idea what that looks like. Would that be accurate? Here. So, let's plug in some points. First of all, we're going to have some limitations on what we can plug in here. Can I plug 5 in? 9 minus 5 squared is going to give you a negative number. What's the biggest number that you can plug in? I can plug in 2. There's a bigger one, though. I can plug in 3. You can take the square root of 0. It's okay. You cannot take natural log of 0. but you can take a square root of 0. Square root of 0 is 0. So if I plug in 3 right here, 9 minus 3 squared will be 0. Square root of 0 is 0. If I plug in 2, I'm going to get 9 minus 4, which is 5. I got square root of 5. If they're making us do this without a calculator, that's not the most helpful point right there. If I plug in 1, I would get 9 minus 1 squared, which is 8. That gives me square root of 8. Again, still not the most helpful point, right? If I plug in 0, I get square root of 9. That is 3. Let's graph what we would have here. I got 0, 3. And I got 3, 0. Set those backwards as I graph them. And then, like, sort of guess a little bit here. I've got square root of 8 is almost square root of 9, right? So it's like above 2. So above 2, and then 1, like somewhere in here. And then square root of 5 is a little more, just a little more than the square root of 2. So that would be 2, a little above 2, and y coordinate of 2, like maybe here, right there. I think, you know, we're just doing the best we can right here. Actually, it's not going to matter how great my graph is, really, as long as I know. I really just need to know right and left on this case. Then I do need to keep going. These two were not all that helpful, but like if I plug in -1, I get the square root of 8 again. If I plug in -2, I get the square root of 5 again. If I plug in -3, I get 0. So I know I got -3, 0 here. This is going to be a perfect semicircle here. I know that because I've done a lot of conic sections. If you square both sides here, you get x squared equals 9 minus y squared. And if you move the x over, you've got x squared plus y squared equals 9, which is a circle, right? We did talk about circles a little bit. But by solving it for x and only using the positive square root, it's only the right side of the circle. So anything that looks like this is a semicircle. It's half of a circle. There. But even if you didn't recognize that, you can at least tell which piece is furthest to the right and which one's furthest to the left. That's the big deal that you need to know here. So now we're looking at this piece right here. That is our base for our region, right? That's the base that we're looking at. Now, here's the problem. I can tell pretty well where these two crossed right here, right? Both of these had the point 0, 3, right? They definitely cross at 3 right here. Can we tell where they cross at the bottom? This bottom point right here? No. It's not perfectly on grid lines. I don't have any numbers that fit both of these right here. But this is a calculator inactive question, so there's got to be a way to come up with that without the calculator. What do you guys think we should try? To see where they cross. We're going to set them equal. So I've got to do the square root of 9 minus y squared equals -1/3 y plus 1. Oh boy. This is where we see what we're made of. What can we do to solve that? A square, because we're definitely not getting anywhere with that square root, right? So 9 minus y squared equals, make sure you got parentheses here. So since this has parentheses, I have to square double square, right, for that. So negative 1/3 squared is positive 1/9 y squared. Then I double by multiplying those two together, which gives me negative 1/3 y, and then doubling it, which gives me negative 2/3 y, and then square the last, which gives you a positive 1. Oh boy. So awful. The fractions. The fractions is what makes this so hard. What type of function is this? It's quadratic. So for quadratics, I need to move everything to one side and factor. But moving everything to one side and factoring while you have fractions like this is difficult to do. So my suggestion to you is try to get rid of the fractions first. What could I multiply through by that would clear the fractions out? Like, what could I multiply? Let's go with the biggest denominator. What could I multiply 1/9 by that would get rid of the fraction? 9, right? And that would work with 3 as well, because 3 and 9 would reduce, right? So here's what I'm going to do. I'm going to multiply everything by 9. You have to do both sides of the function. You don't have to do this, but if you do, it gets rid of fractions, which makes the problem easier to do. So I will get 81 minus 9y squared over here on this left side. When I multiply 9 by 1/9, that's just going to be 1, so I'll just get y squared. When I multiply 9 by the negative 2/3, 2/3 of 9 is 6, so I'm going to get negative 6y, and then I'll get a plus 9 right here. So it's still not easy because I've got some bigger numbers, but at least the fractions are gone. Now everything needs to go to one side. So add the 9y squared and subtract that 81. And we're going to get 0 equals 10y squared minus 6y minus 72. Now, I do notice because these numbers are too big. I don't like that 10 in front of my y squared. I do notice they're all even numbers, right? So I would now go through and divide everything by 2 as well, just to get the numbers a little smaller to deal with. So this is 5y squared minus 3y minus 36. Still not great, but better than what we had. And so finally, we have to factor with that 5y. Any ideas on what'll work? Will 6 and 6 work? Or 6 and negative 6? If I put a plus 6 here and a minus 6 here, this will give me 6y. This will give me negative 30y. Not going to work, right? That won't work. Got to try something else. What else could I multiply to get 36? 9 and 4. So, like, plus 9 minus 4, that'd be 9y, and negative 20y, still not 3. I could switch them, but it's going to make the problem even worse. So that one's out. What else? 12 and 3. This is the one that's going to work. I want to put my 12 here and my 3 here, because this will give me 12y and this will give me 15y, and I want the 15 to be negative, right? Because I want a negative 3, so I'm going to put a minus here with that 3 and a plus here with that 12. That'll give me that negative 15, and that'll give me 3y. So, terrible, right? To have to go through all of that. We haven't even done the calculus yet. This is not even calculus. This is 5y plus 12 is going to equal 0. So we'll move the 12 over. 5y will equal negative 12. We'll divide by 5. So here's what we were looking for, y equals negative 12 fifths. And then the other one is just y equals 3, which we already could tell from the graph. We didn't really need that one very much, but there it is if we need it. So this intersection point right here, your y coordinate is negative 12 fifths there. Now, my hope and prayer for you is that you do not encounter this anywhere on the AP exam, where you actually have to do all of this to get it set up. But just in case, we're doing it now so you've seen it done, right? If they give you calculator active problem, everything we've done here is done by just typing it in, right? So much easier. Just type it in. So that makes it much easier. If they give you a graph and label the points, again, you don't have to do any of this. But just in case you run into it, I want us to do at least one like this. So now we've got to think about actually doing the problem, right? I have square cross section, so I'm back to the ones like I had before. So I'm going to take any horizontal section because it says perpendicular to the y-axis, right? Perpendicular to the y-axis means I'm taking a section that's horizontal, and I'm going to call it S. And then with that section, I'm going to build myself a square, and the height of that square is going to be S because it's square, right? So my area formula, A of y, is going to be S squared. All right, just starting with what we started with on those first two problems, the problems we did yesterday. But S is trickier here because S does not equal just one of these functions, right? Because this time, when we're finding S, we want to think, what is my right endpoint right here, and what is my left endpoint right here? And so that green graph right there, that is x equals the square root of 9 minus y squared. And the blue graph right there is x equals negative 1/3 y plus 1. So we're going to take whichever function you land on the right side of S, right? So that is the square root of 9 minus y squared. And we need to subtract whatever we get on the right side, which is over here at, I'm going to put parentheses, negative 1/3 y plus 1. So all of that stuff is our S. You can distribute the negative if you want. You can leave it like this. It doesn't matter. Here, you can't really do much to combine any of that. Sometimes you can combine things, but not here for that. So that is S. All of this stuff that we just found, all of this stuff that we said is S, gets plugged in here. So our area formula is square root of 9 minus y squared minus negative 1/3 y plus 1 squared. Make sure you've got your parentheses right here. You've got to have those double parentheses here on the end if you did not, unless you distributed your negative and dropped those, because like the whole quantity must be squared. And so we don't have to evaluate this one, so we're almost done, right? So we are going to integrate this formula, the square root of 9 minus y squared minus negative 1/3 y plus 1 squared. I'm going to put a dy over here on the end. What is the lower limit for this one? Negative 12 over 5. What is the upper limit for this one? 3 for that. Okay, so always looking, if you have a dy over here, you're looking at the y-axis for those values. It is not 0 to 3, which is what you'd have if you were looking at the x-axis. It is lowest on the y-axis, highest there. And so they told you did not have to evaluate, so this is it. Now, that one feels terrible, but much like the question you did on the warm-up, I think you guys did pretty well on that warm-up question, right? If I give you the calculator, this turns into a much easier question because you don't have to do any of that first stuff that we did. Okay, here. All right, we're going to do one more. This one's going to be calculator active. Okay, a solid is formed with rectangular cross-sections perpendicular to the x-axis. So we're perpendicular to the x-axis. Is this going to be in terms of x or in terms of y? X. So this is like, put me a dx here. Everything's x's, right? So this one's calculator active, so the first thing I would do is I would graph this. I would also probably call these f of x and g of x. And in fact, if you want to, like if this is a free response question and for some reason they do not name these with function names, like f of x and g of x, you can say let f of x equal x plus 3 and g of x equal x plus 1 squared minus 5. I feel like in the last years they've trended towards just using f of x and g of x in their problem to begin with. But if they don't, you can do this, and now you can refer to everything as f of x and g of x. You don't have to do anything extra with that. So, I am going to screenshot this so I can draw on it so we can picture it a little bit better. And you may want to sketch like a real simple graph of this there. Okay, so the first thing I want us to think about is what shape we have for the cross section, because it's different here. Okay, I am going to draw. We're perpendicular to the x-axis, so it does not matter where you put it, but you're going to have like a vertical slice here. This is going to be your S. And then we have rectangular cross sections, but you have to read about this rectangular cross section to see like what the height of the rectangle is. On the other rectangle problem, our height was 3. But here it says the height of each rectangular cross section is twice its base. So the base is this S, right? That base is the S. And whenever you draw this out, the height of that rectangle, what is it going to be? 2S. So whatever length you have for S, you're making the height of that rectangle 2S. So our area formula for that rectangle is S times 2S, which could be written as 2S squared. But we can't leave this with S's, right? We got to change it to X's. So now I've got to come up with what my S is. So we're looking right here at this part that I labeled S. And I need to look at the line that I intersect on the top minus the line I intersect on the bottom. Okay? What do I have at the top of S? The blue graph. Which one was the blue one? x plus 3. And if you want, because you've already called this, because you have already called this f of x, you could just call it f of x, right? Or you can call it x plus 3. Put parentheses around it if you do. And then what's at the bottom of that line for s? We're hitting the green graph, which is g of x. Okay, and again, you can do x plus 1 squared minus 5 if you want, but if you've named them, it's easier to do it with the names, especially since this is calculator active. This is our s. This goes here. So our area formula is 2 times f of x minus g of x, make sure you double close that parentheses, squared. And so that's what we want to integrate. 2 f of x minus g of x squared. We're going to put dx over here on the end. What do my limits need to be? We're going to have to look on the graph. And actually, the limits on these are not very pretty. And that's partially because I came up with the problem. Sometimes they're going to be nicer. If you see something like this and you have ugly limits, make sure you don't round that off, right? You want to keep as much as you can. It's already rounded, but I'm going to hope that if they put it on the AP exam, they have checked to make sure that it's going to be accurate enough to be within 3 decimal places. So I got negative 3.19258. Make sure you're using the x coordinate here because we're in terms of x, right? And then over here, I need this intersection point here, and that is 2.19258. There. And so to find this, I'm just going to type that in. Negative 3.19258 to 2.19258. And since we've defined these as f of x and g of x, I can just do this, and we are getting 301.928. And I really have not been putting units on any of these problems. This is volume. So what kind of units would you have on all these? Units cubed. So feet cubed, inches cubed, whatever. They don't usually put units on these problems, but they could. And it needs to be cubed if it is. Okay, questions? I had said that we might